Hello, this video is about collisions and explosions. Now just as a reminder, if you don't have an isolated system, in other words, if there are external forces present, then we're going to use the impulse momentum theorem, and that's what we've practiced on so far, which says that impulse J is equal to the change in momentum, and we wrote it this way as well on our cards. Make sure those are on your equation cards. But if you do have an isolated system, that is, there are no external forces, you can apply the conservation of momentum, which says that the original equals the final, and that should also be on your card. If we're applying the conservation of momentum, you'll have one of three types of conservation problems that you're going to be dealing with, and that's what this video is about, is kind of defining those three types and giving you an example of each type. The first type is what we call an elastic collision. So an elastic collision is one in which objects do not stick together. They bounce often, and technically kinetic energy is conserved along with momentum. Now energy is always conserved, but in an elastic collision, in addition to momentum and energy in general being conserved, the kinetic energy before and after is the same. And that takes a pretty special kind of collision. A good approximation of an elastic collision is two pool balls hitting on a billiards table. Or maybe the dynamics carts that we use in lab, they're magnetic bumpers hitting. And therefore you have two objects that are hitting and they bounce apart. So you'd start with a momentum, say, of the cue ball, mv, and the momentum of the 8 ball, and you add those together. And at the end, you'd have momentum for the cue ball final and momentum for the 8 ball final. So you start with two objects and you end with two objects. And that's an elastic collision. So we'll have some situations like that. The second type of conservation problem you might encounter is an inelastic collision. And an inelastic collision is one in which the kinetic energy is not conserved, that is usually transformed into heat, and the object's permanently deformed, or they stick together, or maybe both. So two cars colliding in a car wreck would be an inelastic collision. Two train cars hitting and locking together to make the train longer would also be an example of an inelastic collision. So in this case, we start with two train cars, A and B, and train car A has momentum, MAVA, and train car B has momentum, MBVB. But at the end, those two cars lock together, and so their masses add. I just called it the mass of A and B, and they have a common velocity, the common velocity of VAB. So you end up with two objects, you start with two objects, sorry, and you end up with one unified object. And the third type of conservation problem that you might encounter is an explosion problem. So when I think of explosion, I think of a bomb or a firecracker or something like that. And that would be an example of an explosion. So an explosion is one in which you start with one united object, like a firecracker, and then end up with two or more separate objects. So the firecracker explodes and little pieces of paper go in different directions. But it doesn't have to be quite that explosive. It can be something simpler, like a kid jumping off a skateboard. So before the kid jumps, there's one united mass, him and the skateboard together, mass of the kid board, and then the velocity is common also. They have the same velocity, the velocity of the kid and the board together. But afterwards, you end up with two things. You get the kid going one way and the skateboard going the other way. And so you have two separate momenta to add together, the momentum of the kid, MKVK, and the momentum of the skateboard, MBVB. So here we start with one object with one momentum and end up with two objects with two separate momentums. So those are the three types of conservation problems that we're going to encounter, and I'm going to ask you to be familiar with for our next test.